the Heine Borel theorem is a very important theorem regarding compactness in real spaces Rk. We are going to see it first here in this context of the real line. Okay, and what the theorem says is that any closed and bounded interval in the real line is compact. Notice here, we saw already last in a previous video that the opposite is true. In any metric space, a compact set is closed and bounded. Okay, so here the merit of this theorem is that in the real line, it reverses the implication, and you can say, okay, if it's closed and bounded, then it's compact. But be careful here. An important warning is that this is not true in general metric spaces. Let me take note of that warning. This is true, and we will see it in every Rk, but then in general, it's not. Okay. What is true is that a set is compact, then is closed and bounded. Bounded. There we go. Okay. So why is this theorem important? So sometimes it happens when we want to prove a property that the proof is easier in open sets. There is some property that we can prove in open sets, but not in closed sets. So this theorem is saying that you can replace a closed bounded set, because it's compact, by a finite number of open sets that are the finite cover for that closed interval. Okay, and then you can work in each of these open intervals and complete your proof. Okay, so let's see the proof. The proof is very neat. It uses in a very clever way the least upper bounds property of the real numbers. So proof. So we have here a compact interval, right? Let's say our interval is AB, okay, and it's closed and bounded. Sorry, we don't know yet that it's compact. So to show that it's compact, we need to show that from any open cover that we are given, we can find a finite subcovering. Okay, so let's say, assume we have an open cover with sets O alpha. Okay, this is an open cover of AB. Okay. Now we need to show that we can extract a finite subcovering. Now notice here the alpha. This doesn't need to be a countable set. Okay, this set of indices may very well be uncountable. We may have an open set for each and every point of the interval AB. Okay, so we have no control on that. Now, here comes the neat idea. So we are going to define the set P that is the set of all points in the interval AB such that the interval from A to P has a finite subcover from the O alpha. Okay, so notice here we have we are saying P. Okay, so what we are saying here is we have our interval, right? Here we have A, here we have B, and somehow we are saying that there should be some P somewhere, such that for that P, we will be able to find a finite subcover. Okay, here we have our subcover. Okay, and then the question here is, well, is this going to is this made this P be equal to B? So is there any chance that this is the whole, that it works for the whole interval? So let's see about that. So our goal here, let me state it clearly, is to show that P equals AB. Capital P equals AB. Okay. And we are going to do this in 3 steps. Step number one is to show that we can start this process. We are going to show that P is not empty and that P has a least upper bound. Let's call it lambda. Okay, the second step is to show that the least upper bound lambda belongs to the set capital P. And the last step is obviously to show that the least upper bound lambda equals B. Okay, once we have this, if lambda equals B and we know it's an element of P, then from these two, we get right away what we wanted, right? So we get that B belongs to P, and because of the definition of P, you see here, the point such that the interval AP has a finite subcover, then we will be saying, okay, the interval AB has a finite subcover of the original open cover that we were given. Okay, so that's the layout of the proof. So I was saying, yeah, and there is a finite subcover of AB. Okay. So here, this definition of P maybe will carry it down. So let's start so that we have it for reference. Let's start with step number one. Show that P has a least upper bound lambda. Okay. So the first thing we need to show here is that P is not empty. Okay, remember, first thing we need to show it's not empty. Second thing we need to show it has an upper bound. Okay, so how do we show that it's not empty? Well, actually, this is easier than it looks because A belongs to P. Okay, A belongs to P because the interval AA, which is the single point A, right, has a finite subcover. Why so? Because any set that you pick in the open covering, let's call it O beta. Okay, this is in our original collection. Any set O beta such that A is contained in O beta Will do. Okay. And you might argue, well, how do you know there is any of these? Well, so there is at least one of them. Why? Because the original open cover covers the whole set AB. So it has to cover the point A too. Okay, so the original open cover covers the whole AB, including A. Okay, so it's not empty. We are good here. Now, the second step, 1.2, is to, once we show that it's not empty, we need to show that it's bounded above. Okay, let me copy again the definition. Or just bring it with me. All right, so P is bounded above. What is an upper bound here for P? Well, B is an upper bound. B is an upper bound for P. Why is B an upper bound for P? Well, because P is a subset of AB, then for sure this P I wrote here, it cannot get any larger than B itself. Okay, if it did, it would be outside of the original interval. That cannot be. So we conclude that all the elements in P are going to be less or equal than B. Okay, that makes sense. So then we can invoke the least upper bound property of the real numbers. Okay, and we know that there exists some lambda that is a least upper bound of P. Okay, so here we have the first step. We have shown that P has a least upper bound. Now, step 2. For step 2, we want to show that lambda belongs to P. Okay. So here, what have we seen already in the previous step? We have seen that our lambda has to be at least as large as A, okay, because we saw that A is in the set P. So it will be that one or larger. And also we saw that it cannot be larger than B because B is an upper bound. So we have seen that lambda is in between A and B, or if you want, we can say that lambda is in the interval AB. Okay, so here the question remains, is it in P, then is it going to be smaller or equal to B? So let's do first things first. Let's show that lambda belongs to P. How do we do that? So again, looking at the definition, we need to show that the set, the interval A lambda has a finite subcover of the original open cover. So let's copy this. There we go. So we need to show that the interval from A to lambda, the closed interval, has a finite subcover of the original cover. Okay, how do we do that? Well, here we need to, here a picture will help. So let's say we have our A, B here. Okay. And let's say we have our lambda somewhere. Let's place it there. Okay. What we are going to point out here is that there has to be some interval around lambda, right? Let's call this interval O gamma. Okay, there has to be some interval that contains lambda. Why so? Well, because O alpha is a covering, so it has to cover lambda too. Okay. So let's write that down carefully. So first thing, there exists O gamma in the open cover such that lambda belongs to O gamma. Okay, this is because O alpha covers lambda. Okay, covers the whole interval, in particular lambda. All right. Now, once we have this, it's useful if we write what is the particular interval here in the O gamma. Okay, so we can say this is X gamma, Y gamma. Okay, so we can, in other words, we have X gamma less than lambda less than Y gamma. Okay, so here, going back to the picture, we have our X gamma, our Y gamma. Okay. All right, but now the situation has improved. See what happens. We know that lambda, well, we know that X gamma is less than lambda, which is the least upper bound of P. Okay, so that means, because it's strictly smaller, that means that there exists some number R, okay, that is in P, such that XR less than, X gamma less than R less or equal than lambda. Okay, what does that mean? Well, that means that we can pick some R here, okay? And we can pick this R because X lambda is strictly smaller than lambda. It leaves some space. Otherwise, we wouldn't be able to do that, okay? But now here's the magic. Now this R belongs to P, okay? Because it belongs to P, looking at the definition here, let's bring it here. So R belongs to P means that the interval AR has a finite subcover of O alpha. Okay, so that means that the interval AR can be covered by a finite number of open sets. So we can call this O1 through ON. Let's call it like this. Okay, but we are done, because notice what happens here. Let's copy the picture we already had. Okay, and we have this interval like this. There we go. This is covered by O1 through ON. Okay, and you see what's happening there? So if we take the cover O1 through ON, this covers all the way up to, this covers from A to R, and then we toss in O gamma, this covers from R to lambda. Okay, we are done. We are covers the whole thing from R to lambda. Okay, and this is clearly a finite cover, and this is a subcover, finite subcover of the original one. Okay, so that means that lambda belongs to P, which is what we wanted to show in this step. Okay, now step 3 is to show, once we know that lambda is in P, we need to show that lambda actually equals B. We are going to prove it by contradiction. So okay, so let's assume that lambda is different from B. Okay, so we know that lambda is lesser or equal than B, so that means that lambda needs to be strictly smaller than B. Okay, but if lambda is strictly smaller than B, then there exists a point S, okay, that is just like in the picture. Okay, it's a point such that S is in between lambda and the y alpha we defined before. Okay, it's the same interval O gamma. I think I said alpha, I meant gamma. The same point y gamma that was one of the endpoints of the open interval O gamma. Okay, and then it's basically the same thing as before. So now we have that S is also covered by the previous covering that we found from O1 to ON, and then toss in O gamma, and this covers the whole thing. This covers, you see here in the picture, it would cover R, but it also covers S. Okay, so what is the upshot here? S actually belongs to P. Okay, and by definition, S is larger than the least upper bound. Okay, and this is a contradiction. It cannot be. Okay, so from here we conclude that lambda has to be equal to B. That means that A lambda equals AB, and because of the way we have defined the set P, it has a finite subcover, and that's it.